Okay, hello guys. This is introduction lesson of algorithms and data structure. We will start with numbers and operations on the numbers. So first off, as we know, the numbers themselves are just data. They are not information. So what's the difference between them? For example, we have a 25, this number. 25 is just a data. We don't know, that means whether it represents money, it maybe represents age, it maybe represents temperature or something else. However, when a number comes together with some kind of label or parameter, it becomes the information. For example, 25, it is temperature. This is full information. So because it represents temperature's value. Working with this kind of information through the numbers is one of the most important and fundamental ideas behind algorithms. So firstly, what does it mean algorithm? We can see in here algorithm is total process. Algorithm is the actual sequence of steps used some kind of the problem. It can be written as a natural language, maybe as mathematical formula or any kind of the computer code. The most important thing is that how our approach to the best way to solve the problem before the technical problems. This is also a process of the algorithm. In this process, we can see that algorithms, they receive some kind of the information as an output. It performs a sequence of operations, and then finally it returns some kind of the result. And there are two main requirements of the algorithms working correctly or incorrect. Which one is? Firstly, after the output is given, an algorithm is executed, and then output have to match the executed result. Executed or expected result. This is the first rule. And the second one is, after completing all of the steps, the algorithm needs to stop. At the same time, we know there are different types of the numbers as well, such as it can be digits, natural numbers, real numbers, like the whole numbers, integer numbers, and etc. Which, like the types of the data types we choose depends on the problem that we are solving. For example, if we are working like with, as we say, temperature, we usually use the float types of the numbers. And then, because it can have the values such as 36.6 or any kind of the, for example, -10 types of the numbers are also float type. It can represent these values. And then in the informatical, like the algorithmic point of view, based on these data types, we can look at the structure of the numbers as well. We know that numbers are made up with the digits. We can see this number is, for example, 1125, and it also represents, and it is also collective from the digits. That numbers are also the elements from the any kind of, as we know, the digits are from 0 to 9. And for instance, this number shown here, we can split into ones, tens, like ones, tens, hundreds, thousands, and etc. As a consequence, we represent these place values using a radix in the algorithms, and also known as numerical system. So we can see the real examples of the numerical system in here. Yes, number system. They are represents mainly the four types of the numerical systems, which are a binary system, octal system, decimal, and hexadecimal. One of the most famous system is binary, as we know. Its base is 2, and it usually uses the digits 2 tabs, which are 0 and 1. As a real example, we can see, we can just convert the number, like for example the 15, into the binary format. To do this, we should ask two main questions. Firstly, is this number exactly equal to power of 2? Like power of 2 of 2, maybe power 2 of the 5, or etc. And the second question is, can the number be represented as the sum of different powers of the 2? Firstly, we have to split with this number 15 with mathematically, which is, for example, 15 is represents 32 plus 16 and plus 2. Here we can see, if we sum this and calculate these numbers, it also equals to 15. And we can split again with numerical, with the binary format. What kind of the number, like the power of the 2 is represents 32? As we know, 2 power of 5 is equals to 35. 16 also 2 power of the 4, and 2 is 2 power of 1. So from an algorithmic point of view, we represent the numbers using bits, we usually call. The highest power is 5. We write like the powers from 2 power of 5 down to 2 power of 0, like 5, 4, 3, 2, 1 and 0. This is just one of the simpler example and the simpler explanation of the representing bits. Like 2 power of 0 is participated in here to collecting and to representing 15. In here, no, we can write down in here 0 if it's not represent, and it's not the participate. If it's participate, we can write 1. 1 power of 1 is also represents or not? Yes, the answer. That's why we can write down in here the 1. And 2 power of 2, not, we can write 0. 2 power of 3, no. 2 power of 4, yes. And 2 power of 1, yes. It means the binary system is equals to 11, 0, 0, 1, 0. This means that the decimal number 15 has been converted into a binary numerical system. And also the octal and decimal system also works almost the same. So we will see more samples when we start to exercises. So let's move on and the bitwise operators. These operators usually call bitwise. These are states for AND or XOR and NOT. So let's start from the AND operator. This operator, almost all of the operators compares 2 bits. For example, this is the first and the second bit, and this is the output. So, and firstly, it also compares 2 bits and it returns true or false usually. True means true means 1, 0 means false. When the rule is simple for the AND operator. When both bits are equals 1, then output equals 1. Like it means true and true becomes true. Other all of the cases it becomes false. Like when both sides are false, or either parts of either side is a false, it becomes the false as well. Like another representation, false and true, true and false, false and false, both becomes false. When both sides are true, then it becomes true. OR operator also compares 2 bits, but the main difference is when we compare 2 bits, this also will be true because of both sides are true. When just either one side is true and other side might be false, then it also becomes true. This is the main difference, like true and true equals true, and false true, true false parts comparisons also becomes true. When both parts are false, then the result also becomes false. So we have another operator as well, which is the exclusively OR. It stands for, like, as I said, exclusively OR, which means if the two bits are different, and then it returns true. Like when one side true or true and false, or false and true, then it represents true. Other all of the same cases, it represents false. It needs to be different positions or different representations. 2 becomes true or 1. So not operator is, as its name, its logic is also simpler than others, that it works with only one value. Its job is to reverse just every bit. When one side is 0, then it becomes 1 or false, or opposite. When one side is true and the other side, it represents false. So this is a bitwise operators. Now we can see one of the last operator, which are the left and right shifts. We can also have one of the famous operators, also this one, left shift, sorry, this is right and left shift. The idea is simple. There are two main types of this, left and right, which are, firstly we can see the right shift, as we can see. So right shift operator moves all bits to the right. Left shift operator moves all of these bits to the left. For instance, for the right shift, we have, for example, 10 or 1 and 0. This is a bit, actually, it's not a number. When we want to shift it one bit, we can just, as a simpler understanding, we can just remove the bit from the right. Then it becomes just a 1. Another example, when we write down in here 100, like the 101 bit, and we are shifting 1, again we just remove the last part from the left, and it becomes 10. When we write again 1010, shifting by, for example, 2, we just remove last 2 bits, and it becomes 10. Simple example. Left shift also working almost the same, but opposite direction. It moves all bits to the left. Like, for example, we can see here again 101. We are shifting just the 1 to the left. We can just add 1, means just the 1 0, like 101 before, and after we are shifting 1 left, 101 and 0, 1 0 1 0. When we are shifting by 2, it means we add like double 2. The more we are shifting to the left, the more we add the zeros from the left side. So that one is our main theory parts. We can move on the exercise, which is a practical part. So our first exercise says, like, we need to print the digits of the given number starting from the last digit. Like, for instance, if the input is 1 2 3, like the 1232, the output will be this version, like the reversed but separated version. So firstly, we need to split their digits. For that, input divided by, just as a simple mathematical form, we can just divide by 10. As like the numerical parts, we can see firstly the mathematical form and then the algorithmic form. We have input, we can we can take this number directly, 1232, we can divide by 10. So our main numerical, like the part, number part is, for example, the 10, 32. Again, we can multiply by 2, 20, 32, and 3, 30, and remaining part is 4. This is a remaining part or digit part. And other remaining numerical part, again, we can divide by 10. We can start reversed part, which is 4, like in here, as the same. 123 divided by 4, sorry, 10 again. Again, 1 becomes 10, 23, multiplied by 2, 20, and digit part becomes 3. This is our, we can say, the first our iteration, and this is the second iteration. So it becomes 3, yes, and then the third iteration remained 12. 12 divided by 10, we can multiply by 1 and remained 2. This is also digit or remaining part. This is our third iteration. This also done, we can represent it, and the one of the last is remaining 1. 1 divided by 10 as just a simple the result with mathematical form. We need to multiply by 0, and also our remainder digit part becomes 1. Why? Because 1 equals to 0 multiplied by 10 plus remaining part. We represented all 1 as well. So this is simple mathematical form, and we can convert it algorithmic form. We just need to transform this process into algorithmic. Like when the rule is simple, when input given, we divide it by 10 continuously, and we take the remainder part. It means that our, like these digit remainders, and until remaining numerical parts, when our like algorithm needs to stop when remaining or like numerical parts becomes 0. We can see our solution in here. We need to write the function firstly. We can call it, like for example, print digits, and we are giving argument. We can write firstly the condition, which is like if the input number is 0, then it means we simply just print 0. If number, this argument, input argument, is exact, becomes like the equals to 0, we just need to write print as a 0, and also we need to return it the same result, because we cannot divide it. It also like they just lose the main logic. That's why we are writing this rule or this condition, and then we are writing the main logic in here. So algorithm needs to stop when number becomes like the numbers, like numerical part becomes 0. That's why we are writing while loop number doesn't have to become 0 till firstly, we inside the while loop, the modulo, which is like this symbol, we are like dividing by 10, and we are get only the digit part on, which is a remaining part. That's why we are using this modulo part. So which means digit, our variable, equals to number modulo by 10. This operator returns, as we said, last digit of the number. So, and then we need to print digit, and we are writing the next, the logic is, which is taking the numerical part of the number when we are dividing by 10, which is number, we call it like the integer deviation by 10. So this integer deviation, this operator removes the last digit of the number, as a real example of before we said 1000, like the 232 divided by 2 becomes 122, and then we are continuously dividing by 10, and we are getting this only the numerical parts. To testing them, we just call our function print digits, and we are giving, for example, the input results that we saw before, and we are running it, and it works. We can see 4 3 2 1. If you're writing the opposite number, and when we are tested 1 2 3 4. Now we can see the next exercise, and it says that convert a given decimal number into its binary reversed representation and return as a string format. As we learned, as we saw before in here, the digit or the binary systems represents its and 2, because its base part is divided, they represents 2, and it's usually used with 0 and 1 digits. So again, we can see firstly mathematical solution and then the algorithmic one. We have when our input is 13, our output needs to be reversed version, which is a 1101, which is a binary representation, will be 10 and 11, and then we have to reverse it, and we have to convert as a string format. So firstly, we have to know what kind of the steps it needs to be passing through to reaching the result. We have, for example, we are using as a real example with the 13. We just divide by 2. Why? Because this belongs to the binary representation. And the results will be, with multiplication, we have the 6, and our result, which is the remaining part, 1. And we are keeping continue with the remaining part till our remaining part becomes 0. 6 divided by 2, where multiplication is 3, and then our remaining part becomes 0, and then we're continue with the number part. 3 divided by 2, we're multiplying by 2, and remaining part 1, and the last one, this is the first iteration, second, third iteration, and 1 divided by 2, we cannot give any kind of the numerical part for the multiplication, and our remaining part becomes 1. Why? Because 1 equals 2 multiplied by 0 plus 1 becomes 1. This is a fourth iteration. Till fourth iteration we solve it and we stop it the process. And when we are collecting our digits, which are remaining parts, which are 1, then 0, then 1, and then again 0. Oh, sorry, this is 1. Yeah, this is our result, which are collected our bits. And when we are reverse it becomes 1 1 0 and 1. These results are the same. We can see this is mathematical form. So it's time to see the algorithmic solution. We can see the algorithmic solution. We are writing our function name just with convert to binary, we can call it, and we are giving its argument, which is a number, and again we are writing the condition, which is when it exactly becomes 0, our result needs to be 0 as the string format, and our result also becomes 0. Why we are writing in here? After that, we're collecting all of our digits remainder, which are the remaining parts. We have to collect it within one variable output, and we are writing the while loop is for the iterations until the number deviation part becomes 0. Number doesn't become 0, we can write inside the loop firstly digits, we need to collect it, which are the number divided by, last exercise we divided by 10, but this exercise we can divide by 2 because of the binary representation. So, and then we can write the result part, which is a variable. It's collects all of the digits which are the str string format. It collects remainders digits as a str format as given part, and then we can write the remaining, like the numerical part with the integer deviation that's divided by 2 using integer division. It removes the remainder and keeps only the quotient, like the number part. That's why we need. And our result, it also needs to out of the while loop. It returns results with a reversed version. We can write -1. This is a Python's operation. And to checking for them, we can write the print and our function's name and our argument, which is, for example, 13. The last time our result was firstly 10, 11 and then 11, 0, 1. When we run it and we're checking it, we can see our result 11, 0, 1. When we write just without the reversed version with the result, we can see this reversed, that's simple explanation and representation of the binary. So now we can see the last 2 exercises from the LeetCode, which is LeetCode 7 exercise, the name it reverse integer. So that one is also the same as we solved it before. We can see the given part, given a signed 32-bit integer x, return x with its digits reversed. If reversing x causes the value to go outside the signed 32-bit integer range, like this integer range, then returns the 0. Assume the environment doesn't allow you store 64-digit integers, signed or unsigned. Okay, the examples. When input x equals to 123, output needs to be 321. Example, the next one is when the x just reversed with the negative numbers with minus 123, output needs to minus 321. And when x input is 120, output needs to be 21 because of the 0. We are just ignoring it. So supposing the output we can see as the mathematical form. Firstly, we can see we have a 123 as an input. We just take last digit with, as a simple example, with divided by 10 and take the remaining parts. Remaining part will be 20 and digit part 3. This is a numerical quotient part, and the digit part becomes 3. And then again we take the last digits, which are with the numerical part, divided by 10, and when we multiply by 1, this is our digit, which is a remaining part. Again, the third iteration we can see 1 divided by 10, 0, and remaining part will be 1. And we're collecting with this 3, 2, 1. How we need to represent it as like the 321 to firstly admin. How we need to represent it? Firstly, we move the current result 1 position to the left. It means we need to multiply by 10. Like we have a 3, we need to multiply by 10, and it becomes 30, as we know. There is a empty 1 position then, and we add just a new digit plus the last digit. Like we have a 13, we need to plus 2, then the next step it becomes 32. Then we repeat again the same process, like 32 again multiplied by 10, it becomes 320, and we can move the current result to position to the left. Again, the left part becomes 1, and then our total result becomes 321. The current position to the left, and then last digit we are adding. Main idea is simple. We just need to repeat the 3 steps, not just the 3 steps, mainly in this case 3 steps, till the result becomes 0. The result becomes 0, this numerical quotient part becomes 0. Like, firstly, we need to take the last digit, and secondly, we move the current the position to the left by multiplying by 10, and then we need to add the last digit. We need to add the last digit to the result. So now we can see the algorithmic solution. We have a class named solution, and I will reverse it to the function, and its data type is integer. We use the variable called the sign. Firstly, sign is equals to 1. Why? Because we need to remember whether in this input number was positive or negative. As we know, 1 means the positive. Any kind of a number multiplied by 10 is not changed because of this number is positive. And if the input is negative, the sign becomes like like if our input, which is x, becomes the less than 0, the sign equals to -1, and then x input also becomes to minus reversed version, like the negative version, and our number, and otherwise our number needs to equals to 0 as the given part the represented. If the reversed number goes outside, like the sign at 302 bits integer range, the function must return 0. That's why we're writing number is equals to 0. So the condition, we can write the while loop, while this our input x doesn't becomes to the 0, and our digit, we have to write x divided by 10 and number multiplication and collecting with 10 . It means our first, like the numerical, like the remaining numerical multiplied by 10, then it needs to collect with number plus digit. It means that, like, we can see that as a real example with the 123, we have this result 123 firstly divided by 10, and then we can see that the remaining part, which is 12. Like as we saw in here, we suppose that the input is, for example, 123. Like first iteration happens x equals to, for example, the 123, and our number equals to 0, because we have to collect them after the multiplication and deviation, the total calculation, and digit equals to x divided by 10 we wrote in our code, and then our result becomes 3 as we solve it in here, and number the multiply by 10, it means that 0, that our numerical 0 multiplied by 3, and then the result becomes 0. Okay, if we see the same results, okay, if we see the same process with the same input, like our input is 123 and our number is equals to 0, to calculating after the multiplication or deviation. So first iteration, we divided by 10 and it equals to 3. This is a digit, like the remaining part, digit becomes 3, and number multiplied by, yes, multiplication and equals to 10 means the number plus the digit means like our number multiplied by 10, it becomes 0. And then number part, then the next process digit, it means our number is 0, our digit is, we can see the 3, 0 plus 3 becomes 3. And finally we will write in here that after that process x integer deviation by 10, and then we can write just the number multiplication equals to sign, and just for the positive or the negative side. So the last process we can see in the first iteration that finally in the x integer deviation equals to 10, also as we know it means that removes the last digit, like when our equals to 123 divided by 10, it takes the 12 as we saw the mathematical result in here. This is also the same process. After the first deviation iteration, the result becomes like how x equals to 12, which is this result, and our numerical part becomes 3 from here. And the second iteration, let's keep going from this and finish this total iterations. Second iteration we can see in here. So digit again equals to x divided by 10, not actual divided, like that's word, like the taking the numerical part. 12 by 10 equals 2, and the digit becomes also 2. So then number multiply and equals to 10, our last number was 3 multiplied by 10 equals to 13, and then number plus equals to digit, it means 30 plus our last digit was 2, 32. And then the process is integer deviation by 10, it becomes 12 divided by 10 equals to 1. So after the second iteration we have x equals to 1, which is in here, and our number equals to 32. And third iteration we can see, which is x equals to 1 and number equals to 32. Again we have to divide by 10. 1 divided by 10 equals to, just the numerical part is 1, therefore digit also becomes 1, and then number multiplied by 10, it means 32 multiplied by 10 becomes 320, and number plus digit, our digit was 1, 321, 20 plus 1 becomes 321. And the last one, which is x integer deviation by 10, 1 divided by 10 becomes 0, and when our remained the number part is becomes 0, our loop needs to stop. So and then after the loop, as we saw in our coding part, number multiplied by sign, it's not summing, it's just multiplying. The result becomes negative or positive. That's why we are multiplying them. And the last but not least, we can write the condition parts. But before that, we can check them, it works or not. Yes, it works, but test part didn't finish it yet. We can continue for the checking the bits as well. Like if number is lower than minus 2 power of 31 or number greater than 2 power of 31 minus 1. Then it needs to return 0. Another case, it needs to return the number. And all of the cases are showed the correct results. Minus 123, output is minus 321, and expected result also the same.